Okay, we are at section 25.2, calculating capacitance. Let's look at the PowerPoint, and there's nothing there. Not until I hit the button. And what they're talking about here, you have to. I wish they would have provided an image, but they didn't. If you can imagine a charged sphere, so the C is equal to Q divided by delta V. And for a sphere, Q is equal to KE. We know delta V is equal to KEQ divided by R, but in this case, R is the rate. R is equal to A, which is the radius of the sphere. Well, the Q's cancel, so you have 1 over KE over A, and you can invert the fraction in the denominator. You get A over KE. Well, what is KE? KE is equal to 1 over 4 pi epsilon 0. So if you have that fraction 1 over 4 pi epsilon 0 in the denominator, then that just becomes 4 pi epsilon 0 times A. So that it becomes the capacitance. We usually think of capacitance as requiring 2, but even a single sphere can act like a capacitor, and that would be the capacitance of this charged sphere with the other plate being out in infinity. So it's 4 pi epsilon 0 A. We're not going to come upon a capacitor like that, but that's just for discussion purposes of calculating the capacitance. So when we have a capacitor, when the capacitor is connected to the terminals of a battery, the electrons transfer between the plates and the wires so that the plates become charged. So we know that E is equal to the charge. Sigma is the charge distribution. So E is equal to sigma divided by epsilon 0. Well, the charge distribution is Q per unit area. So it's Q divided by epsilon 0 times divided by A. Q divided by epsilon 0 A. The charge distribution is Q over A. Well, we also know delta V is equal to ED, the electric field times the distance, and that's equal to Q. The E is equal to Q over epsilon 0 A, the area, and then times the distance. So if we combine the definitions of capacitance, Q divided by delta V, which is the QD divided by epsilon 0 over A, you see that the Q's cancel out, and you end up with 1 over D over epsilon 0 A. And again, we have we can take the reciprocal, and we have epsilon 0 times the area divided by the distance between the plates. Now, this is going to become very important. This little blue box, capacitance is equal to epsilon 0 times the area divided by the distance. Because we'll talk about this when we talk about the how you combining capacitors, how you put capacitors in series and capacitors in parallel. We'll talk about these parameters, the distance being in the denominator and the area being in the numerator. So commit this to memory. Capacitance is equal to epsilon 0 times the area divided by the distance. Many computer keyboard buttons are constructed of capacitors as shown in the figure. When a key is pushed down, the soft insulator between the movable plate and the fixed plate is compressed. When the key is pressed, what happens to the capacitance? So if the key is pressed, what's happening? D is becoming smaller. So if D becomes smaller, what happens? Does it A, increase? Does it D, decrease? It changes in a way you cannot determine because the electric circuit connected to the keyboard button may cause a change in delta V. No, the answer is it increases. If you decrease the distance, you increase the capacitance. If D goes down, C goes up. It's inversely proportional. So when the key is pressed, you decrease the D, and it increases. Okay, and that's all for this this section. Next, we'll go to the combinations of capacitors. That's section 25.3.